Welcome. Thanks for joining us for today's presentation entitled Energy Efficient HVAC Systems and LEED version 4, presented by the LEED CE Academy. My name is David Pratt, and I'd like to introduce myself by giving a quick summary of my background and experience. I'm a professional mechanical engineer in the state of Texas and also a certified energy manager in LEED AP. I have a Bachelor of Science in Engineering from the University of Michigan and a Master of Science in Engineering Management from the Air Force Institute of Technology. I have over 12 years of experience in Air Force civil engineering, military construction, renewable energy, and sustainable design. And I'm a frequent contributor to various green building websites, as well as a senior engineer for Aegis Incorporated.
Here's just a quick description of the course. We're going to go over an introduction. We'll talk about HVAC energy as a percentage of total building energy. We'll discuss some HVAC operational costs, which include actual energy costs and O&M, or operation and maintenance costs. And then just a quick introduction on some conventional HVAC system basics. Then we'll get into the meat of the course, where we'll discuss 8 different advanced energy efficient HVAC technologies. Third, we'll speak a little bit about HVAC and green buildings and LEED applicability. And finally, we'll get into a few case studies. HVAC accounts for approximately 15% of all source energy used for electricity production in the United States alone, which results in the release of about 343 million tons of carbon dioxide into the atmosphere every year, according to the U.S. Department of Energy. From the Whole Building Design Guide, heating, ventilating, and air conditioning systems account for 40% of the energy used in commercial buildings in the United States, and the use of high-performance HVAC equipment can result in considerable energy, emissions, and cost savings, anywhere from 10 to 40%. High-performance HVAC can provide increased user thermal comfort and contribute to improved indoor environmental quality. According to the Energy Management Handbook, 7th edition, HVAC systems in most buildings are normally the largest consumer of energy in the building. Fan, pumping, mechanical, and thermal heating and cooling may account for half or more of the total annual energy consumption of a building. Buildings with stringent temperature and humidity requirements, such as hospitals, clean rooms, museums, laboratories, and data centers, may be upwards of 70%. As you can see from the figure on the slide, fans use the most energy within the HVAC system at almost 50%. Airside economizers refer to the use of additional outdoor air when conditions are favorable to supplement or replace the cooling or heating equipment. For example, when the ambient temperature outside is cool, colder than the indoor temperature, outdoor air can be introduced to manage the cooling load instead of the compressor to condition the air. Obviously, this will only work when outside air conditions are suitably cold and/or dry. Drawing in warm or humid outside air will increase the cooling and dehumidification load on the HVAC system, increasing energy consumption. There are typically 4 operating modes for an airside economizer. The first is heating mode. During very cold weather, the air handler brings in minimum outdoor airflow for ventilation and mixes it with the return air. The mixed air is then heated as necessary to maintain the desired supply air or space temperature. ASHRAE Standard 62.1 or building code requirements determine the minimum intake of outdoor air. Modulated economizer mode. During cool weather, between 30 degrees to 55 degrees Fahrenheit, for example, the required space temperature can be maintained without any mechanical cooling or heating by simply adjusting the mix of outdoor air and return air. In this mode, the economizer system adjusts both the outdoor and return air dampers, modulating these airflows to match cooling capacity with cooling load, without mechanical cooling. Intake airflow varies between the minimum setting and a minimum value to maintain the supply air or space temperature at set point. Integrated economizer mode. During mild weather, between 55 degrees to 75 degrees Fahrenheit, for example, outdoor air can provide some cooling capacity, but not enough to satisfy the load, so mechanical cooling supplements the economizer cooling provided by the wide-open outdoor air damper. We refer to this mode as integrated economizer because it combines free cooling, or 100% outdoor air, with mechanical cooling to meet the required cooling capacity. And then finally, mechanical cooling mode. Economizer operation is disabled during warm weather when outdoor conditions exceed the high limit shutoff setting. Minimum outdoor air for ventilation, determined by standard 62.1 or the local building code, mixes with return air. The mixed air is then mechanically cooled as needed to maintain the supply air temperature at set point. According to ASHRAE Standard 90.1, Section 6.5.1, economizer cooling systems must be used in all cooling systems with fans. There's a long list of exceptions to this requirement because the value of economizer cooling depends on climate, building type, system type, and control settings. And it's estimated that about 60% of the buildings in the United States utilize economizers.